Yeah, good afternoon. Let us start the session. So last class we are discussing about various selection techniques, right? So how to select individuals for uh, generating the offspring. That is for the mating pool. So we have discussed. So what are the various selection techniques we have discussed? Could someone recall? What are the various selection techniques we have discussed? So yeah, rank based. So basically, we are totally these six selection techniques are available: canonical, roulette wheel, rank based, tournament, steady state, and Boltzmann. But we'll be discussing five techniques. We'll not be discussing Boltzmann selection. Other five techniques we'll be discussing. So in the last class, we have discussed canonical selection, roulette wheel selection, and rank based selection. So in today's lecture, we will continue with tournament selection and steady state selection. Okay. So basically, canonical selection and roulette wheel selection it comes under proportionate based selection, and rank based is an ordinal based selection. Actually, rank based selection is a small improvement over roulette wheel selection. In the roulette wheel selection, the based on the fitness score, we give rank. Okay, the one with the less fitness score will be given first rank, and then based on the rank, the percentage of space that particular individual will be occupying in the roulette wheel will be decided. Okay, so the topic we'll be discussing in today's class is tournament selection. Okay, so as the name says, it is something like a in a tournament. There will be many participants, and for each of them there will be a match, and whoever wins will go to the next level, and again there will be some competition. Finally, like one winner will be emerging out of the tournament. So that is how any tournament works in the real world. Okay, say for example, one real world example is given here. Say there is some match, say it may be a cricket match or football match or whatever it may be. So these are the countries which are participating. So at the first level, India versus New Zealand. So so out of these two, either any one of the country will win. Okay, so whoever is the winner will come to the next level. Say if India wins, then India will come to the next level. Similarly here, England and Sri Lanka, so whoever wins will come to the next level. If England wins, England will come to the next level. Okay, so here South Africa and Australia, say if South Africa wins, then South Africa will come to the next level. Then then there is a match between Pakistan and Zimbabwe. So assume Pakistan wins, so it will come to the next level. So now there will be a match between India and England. So whoever wins, they will come to the next level. Assume India wins. Similarly, there is a match between South Africa and Pakistan. So this is Pakistan. So whoever wins will come to the next level. Say Pakistan wins. Then in the last level, there will be a match between India and Pakistan. So whoever the winner, they will be declared as the final winner. So this type of so basically this is the way a tournament works, right? Okay. So how this tournament algorithm works, let us try to understand. So first in this scheme we will select the tournament size n. Like first we will select the number of individuals n at random. Okay. Then we pick n individual from the population at random and determine the best one in terms of their fitness. First we identify this n. What is the value of n? N can be either 2, 3 or 10 or whatever it may be. Then we identify n individuals at random and then we determine the best one in terms of their fitness values. Okay. And out of these n individuals, best individual is copied into the mating pool. Thus, in this scheme, only one individual is selected per tournament, and NP tournaments are to be played to make the size of a mating pool equal to NP. Okay. So, what it says in the sense, say for example, the total population is 100. Assume the total population is 100. Okay. Say n is equal to 10. Say n is equal to 10. Then it means that from this 100, you have to identify 10 individuals in random. So these 10 individuals may be any 10 individuals. It may be individual 1, individual 5, individual 7, individual 8. Like that we identify some 10 individuals at random. After identifying the 10 individuals at random, then we identify their fitness score. After identifying the fitness score, then we select only one individual. That is, we select that individual whose fitness score is high out of this 10 individuals. Okay. So whoever the individual whose fitness score is high, they will be moved to the mating pool. That particular individual will be moved to the mating pool. Okay. So that means that in one iteration only one individual will be moved to the mating pool. Okay. That is, in one iteration only one individual will be moved to the mating pool. So if you want to identify NP individuals, then you have to perform this operation for NP times. Okay. So if you want to identify, say if the mating pool size is to be 20, then NP is equal to 20. Then in this case, this operation you have to do for 20 times. Okay. So that's what this algorithm says. So why it is called as a tournament? In the sense, after identifying 10 individuals, say after identifying 10 individuals in each round, out of this 10 we identify the best one, and only that best one with the highest highest fitness score, only that individual will get into the mating pool. Okay. So because of that, it is called as a tournament selection scheme. Okay. So here there is a chance for a good individual to be copied into the mating pool more than once. So this technique found to be computationally more faster than Rowlett-Wheel and rank-based selection scheme. So I think you are understanding this. So there is a chance that an individual may be selected for more than once, because after identifying the best individual, we are not deleting that from the original population. Okay. Say for example, in the first round, the best individual is 7th individual is the best one. Then in the second round also, when I select 10 individual, then the 7 also may come there. And again, if there is no other individuals better than 7, then again 7 may come out. So there are chances that an individual may be copied more than once to the mating pool. So generally this technique is considered to be better than Rowlett-Wheel and rank-based selection scheme. Okay. So whatever we have discussed here theoretically, here it is given as an algorithm. That's it. So in a tournament selection scheme, the input, the actual population size is n, and the output should be the mating pool of size np, such that np should be less than or equal to n. So what we have to do, first select nu individuals at random. Out of nu individuals, choose the individual with the highest fitness value as the winner. Add the winner to the mating pool, which is initially empty. The mating pool will be initially empty. Add this individual to the mating pool. Repeat steps 1, 2, 3 for np times, because we want np individuals, and then stop. Okay. So if you want to say if you want to identify 12 individuals for mating pool, okay, then this algorithm should be repeated for how many times? Yeah, 12 times. It should be repeated for 12 times. Okay. So I want everybody to answer. You can, if you are not opening the mouth, you can also type in the chat. Okay. So here is an example for tournament selection. So n is equal to 8. That is the population size is 8. N is the population size. Nu is, this is in each round how many individuals we are going to select. In each round we are going to select 2 individuals. Okay. NP is also 8. That is after, that is what should be the size of the mating pool. In mating pool we want 8 best individuals. So in this case n is also 8, np is also 8, but in the real world it will not be like that. N will be a huge number. Okay. So so let us assume here n is 8 and np is also 8. So these are the individuals. This is individual 1 and it is his fitness score. This is individual 2, it is his fitness score, so on and so forth up to individual 8 and his fitness score. Okay. So in trial 1, so in each round we have to randomly pick 2 individuals. So in trial 1 we are picking 2 individuals and these individuals are 2 and 4. 2 and 4. Okay. So out of this, the one with the highest fitness score will be selected for the mating pool. So out of this 2 and 4, who is having the highest fitness score? 4. So 4 is selected for mating pool. Okay, in the next round if you see 3 and 8. Out of 3 and 8, who is having the, yeah, 8 is having the highest fitness score. So 8 is selected. Then in the third round, 1 and 3 were selected. Who is having the highest fitness score? 3. In the fourth round, if you see 4 and 5 were selected. Who is having the highest fitness score? 5. In the fifth round, 1 and 6. Who is having the highest fitness score? 6. In the seventh round, 1 and 2. So who is having the highest fitness score? 2. Yeah. Yes. In the sixth round, 2. In the seventh round, 4 and 2. So who is having the highest fitness score? 4. In the eighth round, 8. 8 and 3 were selected. 8 is having the highest fitness score. Okay. So here you can see there is a repetition. Here which individual is repeated? So there is chance for repetition. Yeah, 4 is also repeated. 8 is also repeated. Anything else is repeated? No. Okay. So so even no, even though there are only 8 individuals, here itself there is a repetition. Okay. So if there are many individuals, the I mean, so there will be repetition. Okay. So here it means actually we are rejecting 2 individuals. So which 2 were rejected? 1 and 1 and 7. 7 was never selected, right? 7 was never selected in anywhere. Okay. So and one is very low, so it is never it is never become a winner. Okay. So these 2 were rejected, right? So this is how basically the tournament selection algorithm works. Okay, say for example, if there is such a situation, assume that there is another individual 9. Assume the fitness score of 9 is 4.0. Okay. Assume that, say we are performing one more trial. Say in this trial we are selecting this individual 4 and 9. Now the fitness value of 4 and 9 both were same. Okay. In this case, who will you select? Which individual can be selected? So this is something like a why 9? Any logic? No, but see in a for in normally when there is a tie, what will you do? You can select anything at random. So you have to generate a random number. In this case, you have to generate a random number. Okay. So you can something like a tossing a coin, or you can toss a coin and you can say that if it is head, I will go with 4, otherwise I will go with 9. So, or generate a random number between either 0 or 1. If 0 is selected, I will go with 4, otherwise I will go with 1. Okay, I will go with 9. So that is what it says. If the fitness value of two individuals are same, then there is a tie. So in that case, you can select anything at random. Some randomly you have to select. Okay, there is no generic rule. It is not that we will go with 9 or 4. You create a random number and then you decide which is to be selected. So there are different twists that can be made in basic tournament selection scheme. That is, this tournament selection scheme can be slightly changed to create some other different versions of it. The frequency nu, the small value 2, 3, moderate 50% of n, or it can be as large as nu is equal to n. Okay. So in this case, in the previous example, if you see, nu is equal to n. Sorry, here nu is very small. That is, in each round we are selecting only 2 individuals. Okay. So this is something very small value if nu is equal to 2 or 3. Or you can also choose nu to be 50%. That is, if the population size is 100, then you can say nu is equal to 50. In that case, in each round you will identify 50 individuals. Then from the 50 individual, you have to select one individual as the winner in the each round, and that individual will be added to mating pool. Or you can also choose nu as large as n. So these are the different ways of changing the nu. Once an individual is selected for mating pool, it can be discarded from the current population. So this is also another scheme. See, say for example, 4 is selected. 4 is already selected for the mating pool. So there is no more meaning in keeping 4 again here. So you can remove this 4 from the population. Okay. So that next time you should not create 4 as a, you should not consider 4. Okay. So that means there is no chance for duplication. An individual cannot be selected twice. Okay. So thus disallowing the repetition in selecting an individual more than once. Or what you can do, replace the worst individual in the mating pool with those who are not winners in any trials. Replace the worst individual in the mating pool with those who are not winners in any trials. Sometimes some individual may participate in the tournament, but they will never win because their fitness will be very less. Okay, but in such cases they can be used to replace the worst individual. For example, if you see here 2 and 4, so 4 is the winner, 2 has not won the game. So what you can do is you can use 2 to replace the worst individual. So 2's fitness score is 2.1. Is there any individual with fitness score less than 2? Yeah, 167. So their fitness score is less than 2. So from this, so the algorithm says identify the worst individual. So worst individual means the one with least fitness score. That is 1. So so 2 can be replacing this. That is basically removing 1. Okay. So these are the small variations we can do for tournament selection algorithm. One is trying with different value of nu, and then once an individual is selected for mating pool, it can be removed from the current population. And the third one is replacing the worst individual with those that are not winners in any trials. Here I said for a particular trial, but on any trial. So as a whole, you can see here there may be here one is the one who has not won in any trial, but one is the worst individual. Okay, but assume that instead of 1 here, say 7 is there. So in that case also 7 will not be winning, right? So then you can use 7 to replace 1. Okay, so that is what it says. So that's it about tournament selection algorithm. Next is steady state algorithm. So steady state algorithm, we are not going to discuss anything very deep about steady state algorithm. Just we are going to understand at top level. NU individuals with highest fitness values are selected. Okay, after selecting, that is in each round we select any individual with highest fitness value. Then NU individuals with worst fitness values are removed, and NU individuals selected in the step 1 are added to the mating pool. Okay, so this completes the selection procedure for one iteration. Repeat the iteration until the mating pool of desired size is obtained. So basically the algorithm, how it works, that is we are not discussing that. Say at the end of each round, NU individuals will be selected with high fitness score, and these NU individuals will replace the NU individuals in the population with worst score. Okay, that is in the original population you have to identify NU individuals with worst fitness score, and those NU individuals will be replaced by these NU individuals, and also these NU individuals will be added to the mating pool. They will be added also to the mating pool. So this is what this algorithm says, right? So that's it about steady state algorithm. We are not discussing much in detail. So these are the various selection strategies. Okay, canonical selection, roulette wheel selection, rank based selection, tournament selection, and steady state selection. Okay, so now let us discuss a brief survey on the various genetic algorithm selection strategies. So before that, there is one scheme we will be discussing which is called as elitisms. So this is also one of the scheme for identifying, for generating the mating pool. So this scheme, what it says in the sense, you apply any algorithm, that is you apply any selection procedure which we have discussed. It can be canonical or roulette wheel or whatever it may be. After applying the algorithm, the entire population, divide the entire population into different elite groups. The first elite group will be called as elite 1. The second elite group will be called as elite 2. The third elite group will be called as elite 3. Like that up to elite n. We form different elite groups. So the elite 1 contains the individuals with the best fitness score. Okay, so they are like top class. And the elite 2 contains the individuals with the next best fitness score, something like that. Okay, so assume that there are 100 individuals, then for all the 100 individuals you calculate the fitness score. Okay, say 1 to 10, the one with fitness score 1 to 10 will form elite 1, 11 to 20 will be elite 2, 21 to 30 will be elite 3, so on and so forth. 91 to 100 will be elite 10. Like that we form different elite groups. Then assume that your objective is to identify 20 individuals for the mating pool. Okay, then what we do in the sense, all the individuals from elite 1 will be directly moved to the mating pool. So that is, this 10 individuals will be directly moved to the mating pool. Okay, now for identifying the remaining 10 individuals, we apply any one of the selection techniques which we have discussed above on all these individuals. Okay, on all these elite groups. Is it clear? So what we do in the sense, first we divide the entire population into several elite groups, elite 1, elite 2, up to elite n. Elite 1 will contain the individuals with best fitness score, and they will be moved as such into the mating pool. Still, if the mating pool size is not satisfied, say if the mating pool size is np, and whatever the content you have moved from elite 1 to the mating pool, if it is less than np, okay, then the remaining individual should be selected. Okay, so in this case another 10 should be selected. So this 10 will be selected from the remaining elite groups based on any one of the selection techniques which we have discussed previously. It can be either roulette wheel selection or rank based selection or tournament selection. So that scheme is called as elitism. Okay, So comparing the various selection scheme. So actually all these selection schemes are inspired from genetic algorithm. I mean genetics, in the real world genetics, and which is based on Darwin's principle of survival of fittest. Or you can say that there are two deciding factors which decides the effectiveness of a selection algorithm. There are two factors which decides this effectiveness of a selection algorithm. These are population diversity and selection pressure. Actually these two terms are you can say it is contradictory to each other, or it is inversely proportional to each other. That is, if the population diversity is there, then the selection pressure will be less. If the population diversity is less, then the selection pressure will be more. Okay. If population diversity is high, then selection pressure will be low. If population diversity is low, then the selection pressure will be high. Okay. So what I say in the sense, say for population diversity means we have less number of individuals, and all these individuals are of similar nature. In that case, what will you call? You will call the population as diverse or not diverse? Yes. What will be the diversity score? It will be high or low? Say, is the question is clear? Assume the population contains very limited individuals, and their fitness score is also almost same, it is not much different. So what about diversity? Is it less? Will you say it as less diverse or more diverse? Yes. Am I clear with the question? These are the two factors, population diversity and selection pressure are the two factors which decides the effectiveness of the selection procedure. Okay, and these two are actually inversely proportional to each other. If the population diversity is more, then the selection pressure will be less. If the population diversity is less, then the selection pressure will be more. Okay, so I have a question here. Say the entire population contains few individuals and their fitness score is almost same, then what will you call? Will you call it as a diverse population? What will be its diversity score? It will be more or less? Answer. I think I'm audible, right? So are you understanding the question or not? So I will draw a graph here. Assume this represents population 1. Okay. So these are this population 1, and this x-axis represents the fitness score. I'm calling it as Fs. Okay. Assume that the population 1 fitness score ranges from say 0 to 10. Okay. So this is the various individuals with this fitness score. Okay. So this is something like this. Okay. Assume there is another population P2. This P2's fitness score ranges from 0 to say 70, and it is something like this for different individuals. Okay. So this is something like this. So which population is more diverse, P1 or P2? P2 is more diverse. P1 is less diverse. Okay. Say the number of individuals may be equal. Say for example, here also there may be 10 individual. Here also there may be 10 individual, but still it is more diverse, whereas this is less diverse. Okay. So if the population is more diverse, then there will be less selection pressure, because you have more chances of picking individuals with a different what you call fitness score. So as a result, the offspring can be produced that will be a healthy offspring. Okay. But in this case, the diversity is less. As the diversity is less, there is a pressure, there is a selection pressure, because normally we select individual with best fitness score. So it is highly likely that always the same individuals will be selected again and again. So when you select the same individuals again and again with similar fitness score, the offspring produced also will be similar. Okay, so the convergence, so it may lead to what you call immature convergence, or it may lead to local maxima. All these issues will be created. Okay, so that's what it says. So basically it says that the population should be diverse. The population should be diverse, and also we need more individuals. Then only it is highly likely that in the next round an offspring with a good what you call fitness score will be produced, and the problem also will converge properly, right? Okay, so more population diversity means more exploration. That is, if the population diversity is high, means more exploration. It means you can explore more. That is, you can work on different solutions. That is, you can that is the you can you the I mean the mating pool, the values for the mating pool can come from a big list. Okay, so there are much to explore. Higher selection pressure means less exploration. Higher selection pressure means less diversity, and you cannot explore much. So for example, if you see this, so if you see this full graph, it is actually a good diversity. So these are dots represents individuals. So, and this represents their fitness score. Okay, so these are different individuals with a different fitness score. Okay. So if you consider this full population, then actually it is a diverse population, so selection pressure is very less. But if you assume that you consider only this population, okay, so if you consider only this population, in this range, if you see, actually you cannot explore much. There is only very little exploration, and here actually the selection pressure is more. So whatever you select, for example, you will be selecting mainly from this group, and the offspring also will be similar to that. You cannot produce any better result than this. Right? So these are some observations about population diversity and selection pressure. So population diversity, this is similar to exploration. That is, the extent to which the population is diverse, to that extent you have chances for more exploration. The population diversity means that genes from the already discovered good individuals are exploited, while permitting the new area of search space continue to be explored. That is, you have more space to explore. So there is a chance that you can create better individuals, right? See, one thing you should understand, it is not that, say assume that individual 1 and individual 2. Assume that individual 1's fitness score is very high, okay, and individual 2's fitness score is also very high. It doesn't mean that there, if a mating is done between them, the offspring will have a very high fitness score. It is not ensured. Okay, so there are chances that individual 1 with high fitness score and individual 2 with either less fitness score or comparatively less fitness score will produce better offspring. Okay, so that is what it says. So here we have better chances for exploration. Okay. Selection pressure, on the other hand, selection pressure means that if the diversity is less, then this is similar to exploitation. Then it means that we have only little population, and also their what you call fitness score is similar, then we are only exploiting them. That is, we are again and again doing something similar operation. It is defined as the degree to which better individuals are favored. That is, again and again the same individuals will be selected, because already you have only less individuals, and so in any round what will happen, always we tend to select, the algorithms tend to select the individual with the best fitness score. So always the same individuals will be again and again selected. So if selection pressure is high, then these things will happen. The search focuses on good individuals, right? Yeah, if pressure is high, what will happen? The same individual will be selected again and again. That is less diversity. it loses population diversity. High rate of convergence, it may converge quickly because you are selecting always good individuals. It may converge quickly, but it may result in premature convergence, or it may lead to suboptimal solution, that is nothing but local optima, right? For example, if you consider only this area, no, uh, only assume that the population is only this much, but for the whole problem this is the best solution is available here. But in our case we have not explored all these things, we are working only in this area. So the algorithm will converge quickly. The algorithm will say that this is the better result and I have found it, and it may converge quickly. But actually it is a local maximum, it is not the global maximum, right? So this is called as convergence, and this is also called as suboptimal result, and it is also called as premature convergence. It has converged, but it has converged with some solution, but you cannot say that this is the best solution. So that's what it says. If the selection pressure is high, these things are tend to happen. On the other hand, if the selection pressure is low, so that doesn't mean that selection pressure, if it is low, it has all the advantages. No, it also has some disadvantages. Like if the selection pressure is low, could you tell what could be the disadvantage if the selection pressure is low? If the selection pressure is low, means it is more diverse. Then what is the disadvantage in that? Any idea? See, it will be quite opposite to high pressure. In high pressure, what is the advantage? Advantage is it will quickly converge. Higher rate of convergence. That is an advantage. Are you getting? But it will lead to suboptimal solution. That is the disadvantage. So in this case, what will be the disadvantage? This will be quite opposite to this. Pardon? Okay, means what? If it is not suboptimal solution, then it will lead to what solution? Pardon? Optimal solution. It will give optimal solution. It may give optimal solution. Are you getting? Optimal solution is best solution, right? But it may not converge quickly. This algorithm will converge quickly means what? It will execute fastly. It will execute fastly and it may give the result, right? So that is what is called as converge. Converge means it will come to a conclusion fastly. That means the algorithm will execute fastly, but it will lead to suboptimal solution. Suboptimal solution means it's not an optimal solution. It is a solution, but it is not a best solution, right? But in the second case, it may take long time. It will not converge quickly. It may not drive the search properly, and consequently stagnation may occur. Stagnation means it is opposite to convergence. It may delay long time. It may take long time because the area is huge, because your population is very huge and it is very diverse. So you try with different combinations of mating pool, and you check, you are not satisfying with the solution. This process may happen again and again. Are you getting? So it may not drive the search properly, and consequently stagnation may occur. The convergence rate is low, that is, it will not converge quickly, and GA take unnecessarily long time to find the optimal solution. But maybe after a long time it may find a solution. It may find an accuracy of the solution will increase. Okay, it will finally it will lead to a more accurate solution than this case. That is, if the selection pressure is high. But the drawback is it may take long time, right? So could someone summarize these two things, selection pressure high and selection pressure low? Yes, what happens in these two cases? Selection pressure high, with respect to diversity, what will you say? Yes, I guess you are following, right? See, selection pressure high means it is what it is diversity is less. Okay, diversity is less, that is the population is less diverse. If the population is less diverse, then the algorithm will converge quickly, that is it will quickly identify the solution, but it may not identify the best solution, that is it will lead to suboptimal solution. The solution is not that satisfactory, but as the population is not diverse, we cannot do much. But on the other hand, if the selection pressure is low, selection pressure low means the population is diverse, the population is more diverse. If the population is more diverse, then there are many individuals are there, so there are lot of trial and error you can do with crossover, all these things. So the algorithm will not converge quickly, the convergence rate will be low, and it may stagnate, that is it may take long period to find the optimal solution. But finally it will identify a solution which is of better accuracy than of this case, right? I guess you are following. So could someone summarize these two things? What is selection pressure high and what is selection pressure low? Okay. Hmm. Okay. Fine. Hmm. One more point. Okay. Yeah, Kila, one more point. Yeah, this is selection pressure high means diversity is low. That is fine. Okay. So the algorithm will converge quickly, and also it will lead to what type of solution? So that is it may not give more accurate solution. Okay. Okay. And the other hand, if selection pressure is low, then what does it mean? Diversity is high. Okay. Hmm. Leads to optimal solution. But that is the advantage. But what's the disadvantage? What is it? What will be its convergence rate? Low. That is, it will take long time. It may stagnate. It may stagnate. This point is important. Okay. So these are some of the observations. Okay, with respect to any selection techniques. So depending on the selection algorithm you are choosing, no, based on that you can identify whether its selection pressure will be high or it will be low, in the sense that whether the population will be diverse or not, all these things. So here is a comparison. So if you see Rowlett wheel selection, so here is this table says which selection has more diversity and less diversity. If you see the Rowlett wheel selection, it says that low population diversity. See why we say low population diversity? If you recall Rowlett wheel, actually population may be, we are actually in this case we are not talking about the actual population. We are talking about which is being selected. So in Rowlett wheel, which individual will be highly likely to be selected? More probability means which is occupying high more area in the Rowlett wheel, right? So if there is a Rowlett wheel like this, this is P1, P2, P3, P4 and P5, then who will be selected most probably? P1. Okay, or you can say that P1, P2, P3, any of these three will be selected more frequently. Others will not be selected at all. So what will happen? This is actually less diverse. It is less diverse because most of the time these guys will be selected. These individuals will be selected. Others will be ignored. So this is less diverse. Low population diversity. If it is of less diverse, then it is of high pressure. Okay. If it is low diverse, then it may lead to premature convergence and less accuracy in solution. Okay, right? So, so here the search pressure increases, right? Okay. Rank selection. Rank selection actually, because of this problem with Rowlett wheel only, we are going for rank selection. So rank selection, it actually favors high population diversity. It creates high population diversity, so its convergence will be less and its selection pressure will be low. and it will explore more solution. Okay. Tournament selection population diversity is moderate, ends up with a moderate range of rate of convergence. That is, the convergence rate will not be too fast and also it will not be too slow. It provides very high selection pressure. Pressure is high. Steady state selection, population diversity decreases gradually as the generation advances. Because if you recall, in steady state selection, every time a new individual, best individual we identify and we replace the worst individuals. Okay, so the diversity will decrease gradually because after a period of time, all the individuals will be of similar fitness score. Right? Selection pressure is low. So this is the comparison. And generation gap is defined something like this. Generation gap is equal to P by N, where P is the number of individuals that will be replaced in a given round and N is the population size. Okay. So with this formula, the generation gap can be defined. So for example, if you take a steady state selection with the P is equal to 2 and N of some high value, say N is 100, then if you do 2 by 100, it will be almost close to 0. That is, there is no generation gap at all. Okay. On the other hand, if P is close to N, if P is close to N, then generation gap will be equal to 1, which means there is a good generation gap. Okay. So it means that, assume that initially the population contains 100 elements, 100 individuals. Now you apply some algorithm and you identify some, say best 10 individuals. Okay, 10 individuals, and you are replacing these 10 individuals with the worst 10 individuals from the population. Okay, in this case the the generation gap is 10 by 100, because your population size is N and P is the number of individuals that will be replaced. So that will be the generation gap. So the generation gap is very low. Okay, but assume that the algorithm also produces 100 best individuals. Okay, now what will you do? You are replacing all the 100 individuals with these 100 individuals. Okay, now it will be 100 by 100. That is, it has a very high generation gap. Okay, so basically you understand that generation gap is calculated with this formula, P by N, where P is the number of individuals that will be replaced and N is the population size. So that's it. We'll stop here. So that's it about this selection techniques. So we are discussing different operations, right? So first we have discussed encoding. So encoding is the scheme which is used to generate the initial population, and then we have discussed about selection scheme, which are used to identify the best individuals for the mating pool. Okay, so next we'll be moving on to the next technique, which is crossover. Right. So there are three primary techniques for reproduction. One is crossover, the other one is mutation, and then inversion. So in today's class we'll be starting with crossover. So these are the various GA operations: encoding, fitness evaluation, and selection. So these two things you can combine, right? As a result of fitness evaluation and selection, once the selection is done, the selected individuals get into mating pool. Okay, so there is no separate mating pool thing. Okay, then comes the crossover. So now we are going to discuss about this crossover technique or crossover operation. So this is what we are going to discuss. So basically all these three techniques, crossover, mutation and inversion, they comes under reproduction. And the crossover technique actually it varies with respect to the various encoding scheme. So if you recall, we have discussed different encoding schemes like binary coded GA, real coded GA, tree coded GA, all these things, right? So this crossover is not common for all of these techniques. Actually the crossover technique varies with respect to these techniques. That is, we have a different crossover technique for binary coded GA, and we have a different crossover technique for real coded GA, and we have different crossover mechanism for tree coded GA, right? So first we'll start with the crossover techniques for binary coded GA. So before that, we'll discuss some general thing, mating pool. So how the mating pool is generated. Mating pair is nothing but two individuals or two strings are selected at random. Thus, if the size of the mating pool is n, then n by 2 mating pairs are formed. Okay. So if the mating pool size is n, then n by 2 pairs will be formed. So it's obvious, right? The pairs are checked whether they will participate in the reproduction or not by tossing a coin. That is by selecting a random number, whose probability being PC. If PC is head, then the parent will participate in reproduction. Otherwise, they will not participate. Okay. So if the mating pool size is 100, then there will be 50 pairs. Then for each of the 50 pairs, we have to identify whether they will participate in the reproduction or not by tossing a coin with the probability of PC. So whenever there is a head, they will participate. Otherwise, they won't participate. Okay. Generally, we assume PC is equal to 1, which means that everybody will participate in the process. Okay, so that's what it says. So what is crossover in general? Once the mating pool of mating pair are selected, they undergo through crossover. Okay, so from mating pool we form mating pair. After that, it will undergo crossover. So in crossover, basically what we do, there is an exchange of properties between two parents, and as a result of which two offsprings are produced. Okay, so this you have to understand. That is, with two parents, not one offspring, we will produce two offsprings. Okay, that is with parent 1 and parent 2. When they perform crossover, the resultant will be two offspring. Okay, it's not one offspring. So there will be offspring 1 and also offspring 2. Okay, so both these offspring will have some of its properties from P1 and some of its properties from P2. Right? So a crossover point will be selected, and this crossover point is called as K point. So it can be either 1 point or more than 1 point. So here you can say there is a S, which means that crossover points. So it varies depending on the algorithm. So we select either a single crossover point or more than one crossover point. So in generic, this is called as K point. So using some random number generation, these K points will be selected in between 1 and L, where L is the length of the chromosome. Okay, so this individual, so chromosome is nothing but a string. In this case, if it is a binary coded, it is a binary string. So we generate a crossover point. It can be either 1 point or more than 1 point, and that points are called as K points, such that K lies between 1 and L. Then we perform exchange of gene values with respect to K points. So this is the generic algorithm, like how crossover works. Just try to understand. So what it says in the sense, with two parents we will produce two offsprings, not one offspring, and for every parent we'll identify crossover point. It can be either 1 point or more than 1 point, and this crossover point is called as K points, which lie between 1 and L. And then we perform some exchange of the gene values to produce the offspring. Right? So this is the generic form how the algorithm works. So let us discuss the different crossover techniques which are available for binary coded GA. So these are the various crossover techniques that are available for binary coded GA. There are 8 techniques out there. So we'll be discussing all these techniques, but all these are very simple techniques. You should just understand it. The first is called a single point crossover. There will be only one K point. That is, K is equal to 1. Here the value of K will be 1, right? Not K equal to 1. Number of K's will be only 1. Okay. And 2-point crossover, multi-point crossover, which is also called as n-point crossover, uniform crossover, half uniform crossover, shuffle crossover, matrix crossover, and 3 parent crossover. So these are the various crossover schemes we are going to discuss. Okay. So coming to single point crossover, so this is the algorithm. Before going to the algorithm, let us see the example and then we'll come to the algorithm. That would be much easier to understand. So, consider, say this is parent 1, this is parent 2. Parent 1 is represented through this chromosome or through this binary string, and parent 2 is represented through this chromosome or through this binary string. Okay, so this is the crossover point, that is k is equal to 2. So this is the crossover point. Okay, now how the offspring will be generated, in the sense offspring 1 will be generated something like this, that is the first part of offspring 1 will come from here, from the parent 1, and the second part will be the from parent 2. That is, the first part will be the left part of k of parent 1, the second part will be the right part of k of parent 2. This is how offspring 1 is created. Whereas offspring 2, the first part will come from the parent 2. Okay, that is the from parent 2. In parent 2, whatever which is available in the left of k, that will be the first part of offspring 2, and the second part will be coming from the right part of the parent 1, that is which lies in the right part of k of parent 1, right? So that's it. This is how we perform single point crossover. Okay, now let us see the algorithm, what it does. Here we select the k point which is lying between 1 and L. A single crossover point k on both parents are selected, right? All data beyond that point in either string is swapped between two parents. The resultant strings are the chromosomes of the offsprings, right? So this is how the single point crossover works. So this is with k is equal to 2. Assume that assume that k is equal to 4. So if k is 4 means crossover point will come here. Okay. Then what will be offspring 1? Yes. If k is 1, then what will be, if k is 4, then what will be offspring 1? Zero one one zero 1100. Yes, good. Offspring 2? Yeah, okay. So like that. So like that it will be selected. So it all depends on the value of k. Yes, Abhinav? Yeah. So others also should respond. So this is what supports single point crossover, right? Next we'll discuss about 2-point crossover. In 2-point crossover we'll select 2 points. So what we do here, there are 2 points, k1 and k2. So k1 is something here and k2 is somewhere here. Say k1 is 2, k2 is 1, 2, 3, 4, 5, k2 is 5. Okay. So now what we do, in the middle part, okay, whatever is there, we just swap this. That's all, nothing else. So in offspring 1, if you see, the left part for offspring 1, the left part is coming from the parent 1, and its right part is also coming from parent 1, but the middle part alone, it will come from parent 2. Okay, but for offspring 2, the left part will come from parent 2, the right part also will come from parent 2, the middle part will come from parent 1. That's it. So that is how 2-point crossover is done, right? So in this scheme we select 2 crossover points, k1 and k2, such that k1 is not equal to k2, and k1 and k2 should be lying between 1 and L, where L is the length of the chromosome. The middle parts are swapped between 2 strings. Alternatively, left and right parts can also be swapped. Okay, there is no hard and fast rule that you have to swap only the middle part. So you keep the middle part intact, and instead you swap the right part and left part. That also you can do, right? Okay. So So this is how two-point crossover works, right? Okay, assume that k1 is equal to 2, the same value, k2 is equal to 6. Now what will be offspring 1 and what will be offspring 2? 6 it comes here, right? Yeah, 0 1 1 0. Hmm. Hmm. Yeah, this alone will come from this second parent, right? Offspring 2 1 0 0. Hmm. 0 0, right? Hmm. Yeah. So this is how you calculate, right? So this is what is called as two-point crossover. Next, what we have is multi-point crossover. So in multi-point crossover, you can have more than two points. Okay, it can be 3 points or 4 points or five or n number of points, right? So let us see that this is parent one and this is parent two. These are the various crossover points k1, k2, k3. So here we are considering only 3 points k1, k2, k3. Parent 1 is represented through this symbol. So you can see these slanting lines. This represents parent 1. Okay. This checked thing represents parent 2. So wherever this checked thing comes, it is parent 2. Okay. So now what we are going to do is we are going to swap the alternate sequences. Okay, we are going to swap the alternate sequences. So that is either we swap the even sequences or we swap the odd sequences. Okay, so actually here we are swapping the even sequences. So this is, you can say that this is sequence 1, this is sequence 2, this is sequence 3, and this is sequence 4. Okay, so the resultant offspring, how it is produced in the sense, for offspring 1 we are going to swap only the even thing, not we are not going to swap the odd sequence. So first one is the odd sequence, so it is kept as it is. There is no swapping, right? So from parent 1 it is kept as it is. That is what is the that will be what will be available for offspring 1. Similarly for parent 2, whatever in the first sequence, it is kept as it is, so that will be a part of offspring 2. Coming to the even sequence, this is getting swapped. So whatever in parent 1 that comes to, so whatever in parent 2 that comes to offspring 1, and whatever in parent 1 that goes to offspring 2. Okay. Next again this is a even odd sequence. So we are retaining whatever is in the respective parent. So whatever in parent 1 that goes to offspring 1, and whatever in parent 2 that goes to offspring 2. This last sequence, the fourth sequence, again it is a even sequence. So this part for offspring 1 it comes from parent 2. So here it is checker 1. Okay, and this part for offspring 2 it comes from parent 1. Okay, so like this if you do, that is called as multi-point crossover, right? So could you tell me, so here we swapped the even sequences. Okay, if you swap odd sequences, if you swap the odd sequences, then how will be the offspring? How will be offspring 1 and offspring 2? So, you can answer whether it will be line or what do you call? What will line or checker? For offspring 1, yeah. What different sequences? First sequence will be what? For offspring, first sequence will be checked. Okay. Second second sequence is lines. Okay. Third one is check. Okay, and the fourth one is lines. Right? For offspring 2, first will be you have to swap, right? First will be line. Hmm. Hmm. Yes, okay. So like this it works. So you can also keep some numbers and you can work out, right? It's the same thing. Next is uniform crossover. So uniform crossover is a more general version of multi-point crossover. So what we have discussed previously, so that is multi-point crossover. So uniform crossover is a very generic version of multi-point crossover with some slight changes. What we do here in the sense, at each bit position of the parent string, we toss a coin. That is, we take, we choose something at random, okay, which we toss a coin with a probability of PS to determine whether there will be a swap of the bits or not, okay. So depending on the probability, we decide whether the bits will be swapped among the two parents or not. If the two bits are then swapped or remain unaltered. Okay, so this is how it works. So basically, what we do in the sense, we toss a coin. See this is parent one, this is parent two. So generally, whatever in parent one will come to offspring one, and whatever in parent two will goes to offspring two. Okay. But every time before making this choice, we toss a coin. Okay. While tossing the coin, if the result is zero, so instead of head and tail, we are calling 0 and 1. Okay. So if the result is 0, then we swap. Otherwise, we don't swap. Right. That is, if the result is 1, then parent 1 will straight away go to offspring 1. Parent 2 will straight away go to offspring 2. If the result is 0, then the value of parent 2 will go to offspring 1 and the value of parent 1 will go to offspring 2. Right? So that's what we are going to do here. So this is the binary string for parent 1, this is the binary string for parent 2, and this is the result of the coin toss. This is the result of the coin toss. So for the first, what do you call? For the first bit, it is 1, which means that we are not going to swap. So whatever in parent 1, it goes to offspring 1. Whatever in parent 2, it goes to offspring 2. In the second case, here if you see, it is 0. It means you have to swap. Okay, actually here both are 1. So it doesn't matter whether you swap or not, but still we are swapping. You can understand with this number. So in offspring 1, you got a green one, which is from parent 2. And in offspring 2, you got a red one, which is from parent 1. Okay. And in the third case also it is 0. So you have to swap. So 1 comes to offspring 1 and 0 goes to offspring 2. Here it is 1, so no swap, just move parent to offspring. Here it is 1, no swap, 1, no swap, 0, swap. So this 1 will go to offspring 1 and this 0 will go to offspring 2. This no swap. So in this case you should swap. So 1 will go to offspring 1 and 0 will go to offspring 2. Here also we should swap, but both are zeros. The green 0 will go to offspring 1 and red 0 will go to offspring 2. Here there is no swap. Okay. So this is how this technique works. Right. I guess you are following. Okay. So let me change these numbers, this coin toss number, and you tell me the result. Say this is 0. Let me add more zeros here. So this is also 0. So this is uh, I'll make this 0. I'll make this 1. Okay. Now you tell me what will be for offspring 1. No, no. First bit is what? 0. Okay. Second bit. So let me write here 0. Because this is 0, so it should be coming from parent 2, right? This will be what? 1. This will be 1. This will be, this will be, this will be, this will be, that is coming from parent 2. This will be coming from parent 1. This is, yeah, this is, this is, this is, yeah, okay. So this is offspring 1. What will be offspring 2? This is 0. Why 0? So this coin toss is 0. So it should come from where? Parent 1. So what should be? 1. Yeah, this is 1. Yeah, this is, yeah, this is, this is, yes, this is, yeah, this is, this is 0. Coin toss is 0. So it should come from, this is, hmm, 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 hmm. Yeah. So like this it works. So this technique is called as uniform crossover. Okay. So basically for every bit position of the parent we perform a coin tossing. Okay. So based on the result of the coin toss, okay, based on some probability. So if the coin toss results in 0, then then both the parents will be swapped to create the offspring. Otherwise, whatever in parent 1 will go for offspring 1 and whatever in parent 2 will go for offspring 2. Right? So next is uniform crossover with crossover mask. So this is also one form of uniform crossover, but it is a variation of uniform crossover which is called as uniform crossover with crossover mask. So let us understand this with an example before going to the actual discussion. Okay. So here, so there we are calling it as what you call uh, selecting a probability, but here what we do, when there is a 1 in the mask, when there is a 1 in the mask, the gene is copied from parent 1, okay, else it is copied from parent 2, right, for offspring 1. For offspring 2, when there is a 1 in the mask, the gene is copied from parent 2, else it is copied from parent 1. Okay, so this technique is called as uniform crossover with mask. So this is called as mask. This is a mask. So just understand this. So in the mask, if there is a 1 with respect to offspring 1, the gene will be copied from parent 1. Otherwise, it will be copied from parent 2. Here there is no exchange. There we are exchanging. Okay. Here we calculate offspring 1 separately and 2 separately. Right. And when there is a 1 in case of offspring 2, when there is a 1 in the mask, the gene is copied from parent 2, else it is copied from parent 1, right? So here it is 1. Okay, so offspring 1, this will just come from parent 1, right? This is 0, so it will come from parent 2. Okay, and here it is 0, so it will come from parent 2. So this 1 is coming here. Here it is 1, so it will come from parent 1, so it is 0. Here it is 1, so it will come from parent 1. Here it is 1, it will come from parent 1. Here it is 0, so it will come from parent 2. Okay. Here it is 1, so it will come from parent 1, right? Similarly for offspring 2, whenever there is a 1, it will come from parent 2. Okay, so this is a 1, it comes from parent 2, right? This is 0, so it will come from parent 1. so this one will come here. Here it is 0, so it will come from parent 1, so this 0 comes here. Okay. Here it is 1, so it will come from parent 2, so this 0 will come here. Here it is 1, so it will come from parent 2, so this 0 comes here. Here it is 1, so again it will come from parent 2, so this 1 comes here. Here it is 0, so now it should come from parent 1, so it will come from here. Here it is 1, so it will come from parent 2. So that's it. I think there is no difference between the both the things. Only thing is there it is some based on some probability. So we are tossing a coin means we are generating a random number, right? So every time we generate a random number and we decide. But here this mask is fixed. Based on this mask, this crossover is done. So that's the difference. Otherwise, with respect to working, I guess it is same, because there also whenever there is a 0 we are swapping. So here also it is the same thing, right? The next is half uniform crossover. So what we do here is, so this is the two parents. First we identify the Hamming distance of the parents. Okay, Hamming distance of the parent. So what is a Hamming distance? Hamming distance means, like, for whichever the bit position the parent values are not same. Okay, so based on that Hamming distance is calculated. So here if you see these two bit positions, both the parents were same. Here it is not the same, so just mark this. Again here for both the bit positions the parent values are same. Here it is not same, just mark it. Here it is not same, so mark it. Here it is same, both are 0. Here it is same, both are 1. Here it is not same, so mark it. So now you count at how many locations the parent bit positions were not same. So there are 4 locations, 1, 2, 3 and 4. So the Hamming distance between these two parents is 4. Okay, so this is how the Hamming distance is calculated, right? So the Hamming distance between these two positions is 4. Okay, right? Now what we do, wherever the Hamming distance is what you call, wherever the bit positions are not same, for that locations alone we will toss a coin. We will toss a coin and we decide whether swapping should be done or not. For the remaining positions, the offspring will retain the value from the respective parent. That is, offspring 1 will retain the value from parent 1 and offspring 2 will retain the value from parent 2. So if you take offspring 1, for these positions, based on the coin toss, we will decide like from which parent the value should come. Okay. So in this case, if you see, don't consider this tossing positions. Remaining position, it is just taking the value from offspring 1. I mean parent 1. Offspring 1 takes values from parent 1. This 1 comes from parent 1. This 0 comes from parent 1. This 0 comes from parent 1. This 0 comes from parent 1. This 1 comes from parent 1. Okay. Now for the remaining positions, we have to do a toss and we have to decide. Yes, this also. This. Sorry. So all those black points are coming from the parent directly. Okay. So this 1 is coming from the parent 1. This 0 is coming from parent 1. Okay. This 0 is coming from parent 1. This 1 is coming from the parent 1. For the remaining positions, based on a coin toss, we will decide from where the offspring should get the particular bit from. Okay. So here what we do is, if the toss is 1, then swap, otherwise don't swap. So in the previous case, when the toss is 0, we swapped, but here when the toss is 1, we are swapping. So there is no hard and fast rule, but the algorithm just says that if the toss is 1, then swap. Okay. So here the result of the toss is 1, so swap. Okay. That means offspring 1 will get from parent 2. So this 0, so the 0 of parent 2 comes here. Okay, like here it is 0. 0 means no swap, so it means that for this particular position offspring 1 will get from parent 1 itself. So parent 1 is 0, so that 0 comes here, so it's a red 0 you can see here. For this position again the toss value is 1, so if the toss value is 1 it should be swapped, so it means it should come from parent 2. So parent 2 is 1, so this 1 comes here. Okay, for this position the toss value is 1, so it should be swapped, so it should come from parent 2 which is 1. Okay, similarly for offspring 2, offspring 2 also corresponding to these black positions, it is retaining the values from parent 2. So in parent 2 it is 1, so this 1 here, here it is 0, so it is 0 here. Okay, here it is 0, so it is 0 here, here it is 1, so it's 1 here. For the remaining position it is based on the toss, so wherever toss is 1 it will be swapped, that is it will get from the other parent, otherwise it will get the bit from the respective parent. So it is 1, so it will get the value from parent 1, so this 1 here. Okay, here it is 0, so it will retain the value from its own parent, so this 1 comes here, right? Here it is 1, so it will get from the other parent, so this 0 comes here. Here it is 1, so it gets from this parent, so it's 0. Are you getting? So basically in this case so it is why we call it as half uniform crossover. So in uniform crossover what we do, for all the positions we perform a toss, and depending on the toss value the swapping will be done or not, that will be decided. Whereas in half uniform crossover we are not doing the toss for all the position, we are performing the toss only for the positions where the bits are not in sequence, where the bits are not same, right? Okay. So this is called as half uniform crossover. Okay, so could someone define what is Hamming distance? What is Hamming distance? Hmm. Hmm. That is, you have to identify how many locations the bits of the parents were not matching. You have to count all those things. That is nothing but the Hamming distance. Okay. So let me say there is a parent 1. So parent 1 is given like this 0 0 1 0 1 0 1 1. So parent 2 is 1 0 1 1 0 1 0 0. What is the Hamming distance for this? Why? So this is not matching. This is matching. This is not 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 matching. 1 2 3 4 5 6. Yes, good. So its Hamming distance is 6. Okay, fine. So here what will be the toss should be done at which locations? Yeah, so these are in the first location you have to do a toss, here you have to do a toss, here you have to do a toss, here in all these places you have to do a toss. Okay, only in second and third location we need not do a toss, so that is we have a black shade here only. Okay, so if you take offspring 1, we don't know what is its first value, what is its second what will be its second value? 0. Third value? 1. 4 5 6 7 8 we don't know, let us keep like this. Similarly for offspring 2, first value we don't know, what will be the second value? Third value? 1. 4 5 6 7 8. Okay, right? Now let us say that this is the what you call the result of toss. So the result of toss is this is 1, this is 0, this is 0, this is 1. Okay, this is 0, this is 0. Okay, I'm keeping more zeros for convenient. So when there is a 1, we should swap, right? So here there is a 1. So offspring 1 will get what? From parent 2. Yes. Here it is a 0. So it will come from where? 0 from parent 1. Here it is 0. So what it will be? 1 from parent 1. Here it is 1. So what it will be? 1 from parent 2. Here this is 0. So what it will be? Yes. Again here it is 0. So yes. Similarly for offspring 2, this is 1. So 0 from parent 1. It should be swapped. It should get from the other parent. Okay. This is 0. 1 from parent 2. It will get it from the same parent. 0. This is 0. Next is 0. 0 from parent 2. This is 1. 0 from parent 1. Yes. This is 0. 0 from parent 2. Yeah. This is 0. Yes. Good. So this is how the offspring is created. Okay. So why it is called as half uniform means here we are not doing tossing for every location. We are only doing tossing for the location where the bit positions of the parent do not matches. Okay. So next is shuffle crossover. So in shuffle crossover, what we do, actually it is similar to what you call single point crossover. We identify one single point. Okay. After that, after identifying a single point, we perform some shuffling in each of this what you call in each of this schema. This is called a schema. So after identifying the crossover point, there are different schema. So you can say that this is schema 1, this is schema 2, or this is schema 3, or this is schema 4. Like that, 4 schemas are there. In all these schemas, we perform some swapping or some shuffling. After doing the shuffling, you perform the regular crossover that we normally do in a single point crossover. So that is what is called as shuffle crossover. So here this is the crossover point 1, 2, 3, 4, 5, 6. That is crossover point k is equal to 6. Now the algorithm, there is no specific way for this shuffling. That is you can decide like what you want to shuffle. So here we want to shuffle these things. So that is from parent 1, in parent 1, first bit will be shuffled with third bit, that is it will be swapped, and second bit will be swapped with fifth bit. Okay. Similarly, so you cannot shuffle from one schema to another schema. Within schema you can shuffle. Okay. That is you cannot shuffle this 0 with this one. That you cannot do. Within this schema we can shuffle. Similarly, 1, 2, 3, 4, 5, 6, 7th bit is shuffled with 8 bit. Okay. Similarly, in parent 2, first bit is shuffled with second bit, and similarly here 2, 3, 4, 5, 6th bit is shuffled with 7th bit. So this is the thing after shuffling, after shuffling, but before crossover. Okay, so you can see this 1 and 0 were shuffled. So 0 comes here, this one comes here, and this 1 and 0 were shuffled. This 0 comes here, this one goes here. So this 1 and 0 were shuffled. This 0 comes here, this one comes here. This is for this 1 and 0, and this is for this 0 and 1. Right. Now you perform the regular crossover. So in regular crossover, how we create offspring 1? It will get from the left part of the parent 1 and then right part of the parent 2, so on and so forth. So this is the resultant offspring, right? So this is what is called as shuffle crossover. And the next is matrix crossover. So this is a technique which is used if the string is very long or if the chromosome is very lengthy. So generally it is not used. It will not be used if the chromosome is of shorter length. This will be used if the chromosome is very large. Okay. Say the chromosome is very large, it contains a very large string F112, F1N. So like that, there are two parents. Okay, I1 is there, I2 is there. Both these are very long chromosomes. Okay. Now this long chromosome, instead of representing it as an array, so this is something like an array, right? Instead of representing this as an array, you can represent it as a matrix. That is, you can represent it in rows and columns. Say, assume that you have a chromosome with 100 entries, 1, 2, 3, 4, 5, 6, up to totally the length is 100. So starting from 1 to 100. So instead of keeping it as a this like this, you can represent it as a matrix. You can represent, say, you can represent it as a 10 by 10 matrix. That is, there will be 10 rows and 10 columns. There will be 10 rows and each row contains 10 columns. So this is actually the same chromosome, but now you are representing it in a different way. Okay. So this I1 is represented as P1 and I2 is represented as P2. Right. Okay. Now we decide like which blocks in the matrix will be swapped and which will not be swapped. So we identify certain parts that will be swapped and the rest of the parts will not be swapped. Okay. So here what we do, in the sense, we are identifying these parts. So these parts will be swapped. The remaining parts will not be swapped. Okay. So these are the parts are swapped. So the resultant child, this is child 1 and this is child 2. So if you see child 1 is getting this block from parent 2. Okay. Whereas this block of child 1, it is retained from parent 1 as it is. Right. Similarly, child 1's this block is retained from parent 1 as it is, but this block is coming from parent 2. And child 1's this part is coming from parent 2 and this block is retained from parent 1. Similarly for child 2 also. So child 2, if you see this block, it is coming from parent 1. Okay. And this block, it is retained from its own parent, that is parent 2. And this block of child 2, it is retained from its own parent, whereas this block of child 2, it is swapped, that is, it is coming from the parent 1. Okay. Similarly, this block of child 2 or offspring 2 is coming from parent 1, whereas this block is retained from its own parent, right? So this type of crossover is called as matrix crossover. And the next crossover what we are going to discuss is 3-parent crossover. So in this technique we'll have 3 parents. So normally we have 2 parents, but here we'll have 3 parents. Each bit of the first parent is compared with the bit of the second parent. If both are same, the bit is taken for the offspring, right? Otherwise the bit from the third parent is taken for the offspring. But in this case there will be only one child. So normally with we'll discuss whatever we are discussing, in all the cases there will be 2 parents and 2 offspring. But in this case there will be 3 parent, but there will be only one offspring. That is, we just to compare P1, P2. If P1 and P2 are same, then that same bit value will come for the offspring. If they are different, then the offspring will get the bit position that is available in parent 3. So that's the logic. It's a very simple logic. So here you can see there are 3 parents, but there is only one child or one offspring. So here 1, 0. 1, 0, it's not matching. So the child will get the bit from the third parent. Okay. Both 1 and 1, it is same. So it will get from either from P1 or P2. Right. Here 0 and 1, it's not same. So the child will get from P3, that is parent 3. 1 and 0, it's not same. So the child will get the bit from the parent 3. 0 and 1 is not same. So the child will get from parent 3. 0, 0, it's same. So the child will get either from parent 1 or from parent 2. 0, 0, it is same. So the child will get the value either from parent 1 or from parent 2. 1, 1, it is same. So the child will get either from parent 1 or from parent 2. This is the resultant offspring which is created, right? So this is how this 3-parent crossover technique works. Okay. Or you can also consider the third parent as a crossover mask. We have discussed one technique with mask, right? So in that case you can create 2 offspring also. Okay. If you consider the third parent as a mask. Okay, in mask means you will swap when there is a 1 or there is a 0. Okay, you decide when to swap, right? Uh, okay, so let me change this value for uh, value something. I'll make this 0. I'll make this 1. Okay, now you tell me what will be the child. What will be 0, which is coming from P3. 1, 1, hmm, 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 hmm. Yes, okay. So this is how we create the child. So here there is a both P1 and P2 have common values only for this location and for this location. So only for this location it is coming from either from P1 or P2. Remaining all locations it is taking from P3. Okay. So this technique is called as 3-parent crossover. So that's it about various crossover techniques. So here we have some comments on the binary crossover techniques. So non-uniform variation. It cannot combine all possible schemes. Okay, so based on the what you call crossover point, we are doing crossover. So all possible schemes cannot be all possible combinations cannot be made. For example, it cannot in general combine instances of uh, all combinations of one and like this. Okay, so similarly, positional BIOS. The scheme that can be created or destroyed by a crossover depends strongly on the location of the bits in the chromosome, right? So basically, based on the crossover point, the offspring is created, right? So if the crossover point is 2, then the offspring will be of one type. Otherwise, it will be of another type. Endpoint BIOS. It is also observed that single point crossover trees treat some locations preferentially. That is, the segments exchanged between the two parents always contains the endpoints of the string. So that is obvious because there is only one point. So some endpoint will become the form of one of the child, right? So these are some of the comments or some of the what you call some drawbacks of binary crossover schemes. And then there is a problem with this scheme which is called as Hamming-Cliff problem. This Hamming-Cliff problem, what it states in the sense, sometimes you may change many bit positions in the chromosome, but the result will not. There may not be much change in the result. Okay, the result change will be very little. Sometimes you may change only one bit position, but the change in the result will be very much phenomenal. So this problem is called as Hamming-Cliff problem. A one bit change can make a large jump, okay, a big jump. A multi-bit can make a small jump. It may happen. Here is an example given. For example, say assume this is one binary string or a chromosome 1000. Now assume that we are not doing any logically, we are not changing anything, right? We are randomly doing something. So assume that this is the change done. So actually you are changing every bit. This first bit you have made to 0, second bit you have made to 1. All things were changed. That is, all zeros were converted to 1, all ones were converted to zeros. So there is if you compare these two strings, there is a lot of change. But if you check actually its value, the value, there is no much change at all. This is nothing but 8. Its decimal equivalent is 8. Its decimal equivalent is 7. It's very close. Are you getting? But if you see this, but these two things, this string is all zeros. Here we just made only one change. In the first position we added a 1. Now this is 0, this is 8. So there is a big change. So what it says in the sense, sometimes a small change will create a big difference. Sometimes a lot of change also will make a small difference. So these are some of the drawbacks or issues which are identified with this scheme, right? Okay. To reduce the positional bias and endpoint bias, two-point crossover or multi-point crossover have been evolved. So this positional bias, endpoint bias, all these are the drawbacks with single-point crossover techniques. So to overcome this drawback only, we are going for two-point or multi-point crossover. So if you use multi-point crossover and if you use many points, then obviously you can create child of different combinations. Okay. In contrast, UX and HUX distribute the patterns in parent chromosome, largely resulting too much deflections in offspring. So UX is what we discussed. UX, which is uh, one is half this thing, right? Half uniform crossover. That is based on tossing. We decide like the child will be created from which parent. So that is UX, and the other one is half UX. That is half uniform crossover. So here the drawback is they may create the child which is very much different from the parent. Okay, that it is totally deflected from the parent. Okay, so these are, whereas in case of what you call binary crossover binary crossover technique. I mean single point crossover technique. The drawback is the child is very much resemble to the parent, right? If you recall the single point crossover technique, there is only one point. So most part of the child will come from one of the parent, and other part will come from the another parent. Okay, so it is going to resemble, mostly it is going to resemble any one of the parent, right? So that is what the drawback with the single point crossover. So to overcome that drawback, only 2-point and multi-point were introduced. But the drawback with the UX and HUX is uh, that is uniform crossover and half uniform crossover is the offspring created may be very much different from the parents. Okay. To avoid the binary code related problem, gray coding can be used. So here we used binary code, no. So this is the binary code issue. That is, even you change many bits, the resultant change is very small. Here you are changing only one bit, the resultant change is huge. So to overcome this problem, you can use a technique called gray coding. We are not getting into the detail of this, but this is one of the solution to overcome that problem, right? So in summary, binary coding is the simplest encoding, and its crossover techniques are fastest. So whatever the crossover techniques we have discussed, so far we have discussed the crossover techniques for binary coding scheme. So these crossover techniques are the fastest crossover techniques compared to the other crossover techniques that we are going to discuss. Okay, so they can actually work very fastly, right? So next we will be discussing crossover techniques in real coded GA. So basically there are different types of encoding, right? Binary coded encoding, real coded encoding, tree encoding. Okay. So now what we are going to discuss is various crossover techniques in real coded GA. So it's getting late. I'll give a brief introduction and we'll just stop here. So basically this real coded GA, we have three types of real coded GA. It can be further classified into three types. One is linear crossover, the other one is blend crossover, the other one is binary simulated crossover. So these are the three types of real coded GA: linear crossover, blend crossover, and binary simulated crossover. So linear crossover, if you take linear crossover, it is just given by this formula. So the child is created something like this. So here the parent will take a binary value. So parent 1 maybe it may take some binary value 31.2. Parent 2 will take some other binary value 6.4. Okay. So the child is created like this. Ci is equal to alpha I p1 plus beta I p2. Okay. Where I ranges from 1 to n, that is the number of children you want to create. Alpha I and beta I are some constants. So these constants we have to generate. Okay. So otherwise it is directly applying the constant on that formula. So for example, if P1 is equal to this and P2 is equal to this, and alpha 1 and alpha and beta 1 both are 0.5, okay, and if alpha 2 is 1.5 and beta 2 is minus 0.5 and alpha 3 is minus 0.5 and beta 3 is 1.5, then child 1 is nothing but what? Alpha 1 P1 plus alpha 2 P2. So it is nothing but 0.5 into P1 plus P2. This is the result. Child 2 is nothing but uh, 1.5 into P1 minus 0.5 into P2. That is beta 2 is minus 0.5. So this minus comes here. So this is the result. And this is child 3 minus 0.5 into P1 plus 1.5 into P2. Okay. So here one thing you can observe. What is, say this is the range. The range is between 10 to 25. P1 is 15.65. P2 is 18.83. When you select alpha 1 and alpha 2 to be same, when alpha 1 is equal to, alpha 1 and beta 1, or alpha and beta. If alpha is equal to beta, then the result will be lying in between P1 and P2. Here you can see, in the first case, alpha is equal to beta. So the result, the child is actually lying between P1 and P2, right? Okay. Whereas in the second case, beta 2 is very much lesser than alpha 2. Okay. Beta 2 is very much lesser than alpha 2. Okay. In that case, the child will be lying to the left side of P1, right? In the third case, alpha is very much lesser than beta. In the second case, beta is lesser than alpha. In the third case, alpha is very much lesser than beta. In that case, the child will be lying to the right of P2. Okay, so these are just some observations. So we'll just stop with this slide. The advantage of this technique is it is simple to calculate and also it is faster in computation. It can allow to generate a large set of offspring from two parent values. Okay. So here we created 3 offsprings. Like that you can create any number of offsprings. Only thing you have to try with different values of alpha and beta. So there is a wide range of results is possible. The disadvantage is, actually here the challenge is identifying the right alpha and beta. Okay, need to be decided. You have to identify the correct alpha and beta. It is difficult for the inexperienced user to decide the right values for alpha and beta. If alpha and beta are not chosen properly, the solution may stuck into local optima. So everything depends on choosing the correct value for alpha and beta. So if you identify the right value for alpha and beta, you will end up in global optimal solution. Otherwise, the solution may get stuck in local optimal solution. Okay. Fine. Let us stop here.